Pluto is a distant and cryptic dwarf planet that was previously part of our planetary system. However, recent surprising discoveries by MIT, Neil deGrasse Tyson, and Michio Kaku, two notable astrophysicists, have brought Pluto back into the public eye with an astonishing revelation. They propose that this icy world might be headed for a collision with Neptune. How could this happen, and what might the consequences of such a significant event be? Are we witnessing an extraordinary cosmic phenomenon, or is there more to this fateful celestial encounter? Join us as we examine the potential repercussions of a Pluto-Neptune crash. The astronomical community remains intrigued by and continues to explore Pluto, a former planet that was downgraded to a dwarf planet in part due to its peculiar orbit. According to recent predictions by leading researchers, Pluto's orbit is dangerously close to Neptune. Both Kaku and Neil deGrasse Tyson are concerned about the possibility of a catastrophic collision between these two planets, which could even pose a threat to Earth. But how is such an event possible, given that no other planet in our solar system resembles Pluto? Since Pluto takes a remarkable 248 years to complete an orbit, it hasn't even completed a full revolution since its discovery in 1930. But the wonder doesn't end there. Pluto's orbit is unique in that it is highly elliptical, deviating significantly from the almost circular orbits of larger planets. One of the most fascinating features of Pluto's orbit is how it intersects with Neptune's path for about 20 years in each orbit. Contrary to what one might expect given their positions in the solar system, Pluto actually comes closer to the Sun than Neptune. This raises the question, why hasn't Pluto collided with Neptune? The gravitational pull of other planets provides the answer. Pluto's trajectory is much more inclined than that of other planets due to its estimated 17 degrees tilt to the ecliptic plane. Unlike the orbits of most planets, which remain close to the ecliptic plane, Pluto's orbit was first studied by scientists shortly after its discovery to determine its unusual path. Due to its long shape and high inclination, Pluto's orbit was distinct, and the fact that it still crosses Neptune's orbit added to the mystery. The stability of Pluto's orbit, despite these challenges, is evidence of the complexity of space mechanics. Understanding how three objects like Pluto, Neptune, and the Sun move and interact through gravity is known as the three-body problem in astronomy. This is similar to trying to predict the future locations of these objects based on their initial positions and the forces they exert on one another. In Pluto's case, this problem demonstrates how its orbit interacts with the Sun and Neptune's gravitational pull. Terms like alpha libration, scope libration, and VZ oscillation are used in this context. Astrophysicists believe that a process called alpha alignment maintains the stability of planetary orbits. In the case of Pluto and Neptune, this means that Pluto remains approximately 90 degrees away from Neptune, and this distance is crucial for preventing their orbits from colliding. When Pluto approaches, it is well above the orbital plane of Neptune or any other massive planet, providing an extra layer of protection against potential collisions. Libration refers to the vertical movement of a celestial body within its orbit. Another significant factor in this scenario is the VZ oscillation, named after three space scientists, Bond, Zippel, and Kai. It describes how the gravitational attraction of the Sun, Pluto, and Neptune on each other is explained. Understanding how these orbits evolve due to the forces these celestial bodies exert on one another is essential to solving the three-body problem, which in turn helps us learn more about Pluto in our solar system. This oscillation explains why Pluto's orbit around the Sun is so unusual, even though it appears to follow an erratic path. Despite the chaotic and seemingly random nature of space, it has maintained stability for billions of years. These factors also help Pluto remain in its orbit, preventing it from colliding with Neptune or deviating from its course. Studies on stars and distant worlds have shown that these unique aspects of Pluto's orbit ensure stability over extremely long periods, effectively controlling chaos. In fact, mathematical simulations conducted in the late 1980s have shown that we now understand more about how giant planets like Saturn affect Pluto's orbit. Pluto's orbit is highly chaotic, with small variations in initial conditions leading to significant fluctuations over thousands of years. New computer models show that Pluto's orbit around the Sun is influenced by Jupiter and Neptune due to a special interaction between the planets. Pluto completes one orbit around the Sun for every 2 Neptune completes. Yet, Neptune is not the only factor maintaining Pluto's orbit. It appears that Neptune, Jupiter, and Saturn work together to keep Pluto moving through space safely and without issues. Free tests indicate that Jupiter's gravity alone is sufficient to keep Pluto on a stable course for a long time, perhaps billions of years. Saturn also plays a significant role in maintaining Pluto's orbit. In the grand scheme, these phenomena are crucial for maintaining order and consistency in the movement of celestial bodies. Without them, the solar system would be far more chaotic and unpredictable. For instance, Pluto could collide with other planets or be ejected from its stable orbit, which could have profound effects on other celestial objects. This is particularly relevant considering discussions surrounding Pluto's potential future collision with Neptune. By understanding Pluto's orbit, we can better comprehend the dynamics of the solar system. Exploring the depths of space often brings us face to face with the eccentricities of celestial bodies, and Pluto's orbit is a prime example of this uniqueness. The Pluto phenomenon also emphasizes the importance of continuing to observe and study these occurrences to better understand our place in the cosmos. Since its discovery in 1930, Pluto has undergone extensive study, which has yielded significant discoveries about its composition and behavior. Even slight changes in the dwarf planet's position or speed can drastically alter its long-term trajectory. In the vast realm of our solar system, Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Pluto's orbit serves as an example of how even the seemingly most unstable orbits can achieve a state of harmony through the intricate interplay of gravitational forces and orbital mechanics. One of Pluto's generally striking qualities is its surface. It is an intricate mosaic made of ice, rock, and different components. Astonishing facts about Pluto were discovered during the New Horizons mission's July 2015 flyby. The planet's surface is made up of vast fields, tall mountains, and deep valleys. Sputnik Planitia, an enormous heart-shaped plain primarily made of nitrogen ice, is one of the area's most distinctive features. Enormous ice lumps and what appear to be moving glaciers are among its topographical characteristics. These highlights suggest that Pluto, despite its extreme cold and distance from the Sun, may still be geologically active. Pluto's atmosphere is another fascinating aspect. Although Pluto has a thin atmosphere, it shows captivating seasonal variations as it approaches the Sun in its long orbit. This dynamic behavior reflects the complex relationship between Pluto and its atmosphere, as certain gases may freeze onto the surface during Pluto's closest approach to the Sun and then sublimate back into the atmosphere as it moves farther away. Pluto's atmosphere is primarily nitrogen with traces of carbon monoxide and methane. Pluto shares a unique relationship with its largest moon, Charon. Since Charon has a diameter that is roughly half that of Pluto, the two bodies orbit a mutual point in space rather than Pluto merely orbiting Charon. This unique relationship affects the local gravitational dynamics, which in turn influences the orbits of other objects in the Kuiper belt. Numerous more dwarf planets and possible impactors may be found beyond Neptune, which is populated by tiny icy worlds. It also contains ancient material from the early solar system that can help scientists understand its formation. The orbital patterns of these distant objects may be revealed by Pluto's orbital properties, suggesting that encounters with larger planets may have significantly influenced their current orbits. The potential impact on our understanding of the solar system's evolution is among the most significant consequences of studying Pluto's orbital dynamics. Research on Pluto also raises philosophical questions about cosmology and order. Pluto's 2006 reclassification as a dwarf planet sparked discussions on what defines a planet. Many people considered the implications of such classifications, as the definition provided by the International Astronomical Union emphasized factors like size and orbital dominance. Smaller worlds, particularly those in the Kuiper belt, may experience changes in their paths due to the gravitational pull of nearby massive planets like Jupiter and Neptune. These interactions may result in orbital shifts that could lead to collisions or ejections from the solar system. Given advancements in technology and mission planning, scientists are optimistic about exploring Pluto and the Kuiper belt in the future. This ongoing debate also highlights the need for a flexible approach to defining celestial bodies, reflecting our evolving understanding of the universe. Envisioning the launch of more spacecraft to examine Pluto and other objects with similar orbital characteristics is an exciting frontier. Another intriguing field of study related to our understanding of Pluto is the role of exoplanets, or planets outside our solar system. As astronomers discover more exoplanets, particularly in the habitable zones of their stars, these missions may yield valuable information about the primordial materials that formed our solar system, possibly providing clues about the origins of life on Earth. Our understanding of patterns within our own solar system can aid in the development of theories regarding planetary formation and habitability conditions that allow for stable orbits. People around the world are inspired by Pluto's intriguing nature and the stunning images returned by the New Horizons mission. Geologic activity and atmospheric retention may also offer insights into the potential for life elsewhere in the universe and a greater appreciation of the vastness of space, and our place in it, as we strive to address the enduring mysteries of the universe. The mysteries surrounding Pluto and the other celestial bodies in its region serve as a constant reminder of the wonders the universe holds. Beyond its physical properties and orbit, Pluto has unique qualities that make it an excellent case study for understanding the dynamics of celestial bodies and planetary formation. It is believed that Pluto and other Kuiper belt objects underwent evolution in the early solar system. Research into its composition could provide information on the conditions that prevailed in the early solar system, thus challenging assumptions about how terrestrial planets came to be. Certain areas of Pluto's surface, such as the frozen mountains, may be made of water ice, which behaves differently from typical rock at low temperatures. According to recent data from the New Horizons mission, this finding raises interesting questions about the potential for life even in such extreme conditions, which could alter our understanding of Pluto's geology and its ability to support life. This also encourages further investigation into the possibility of liquid water beneath Pluto's icy crust and its interactions with its surroundings. The significance of continuing to monitor Pluto and other similar celestial bodies cannot be overstated. With more missions planned, especially those focused on the outer reaches of the Kuiper belt, we can expect a wealth of new data that will challenge current theories and expand our understanding of planetary science. Through these efforts, every discovery adds another piece to the puzzle of the history of our solar system and the mechanisms governing its evolution. Pluto's thin atmosphere and seasonal changes provide a planetary-scale natural laboratory for atmospheric dynamics research. Scientists are particularly interested in how complex weather patterns, similar to those seen on larger planets, could arise from the interaction between solar radiation and the surface. Pluto still serves as a symbol of the unending quest for knowledge about the universe, inspiring both scientists and the public to contemplate the mysteries that lie beyond our solar system.